Welcome back. Today, we're diving deep into the heart of hydronic systems, distribution piping. This is where the rubber meets the road, or rather, where the water meets the pipes. We're going to look at how we actually get heat from the boiler to the rooms that need it, and how we control that heat efficiently. You know, people often obsess over choosing the perfect high-efficiency boiler, but here's the thing the author emphasizes. You can have the best heat source in the world, but if your distribution system is poorly designed, that boiler is crippled. It's like putting a Ferrari engine in a go-kart. We need to focus on the piping to make the system work. Let's start with zoning. A zone is just any area controlled by a single thermostat. Multi-zone systems are great because they let us control comfort room by room and save energy in unoccupied spaces. But, and this is important, don't just add zones for the sake of it. Too many zones can actually cause problems, like boiler short cycling and unnecessary complexity. Now, here's a concept that trips people up: thermal mass. Clients often think if they turn the thermostat down, the room cools instantly. It doesn't. If you have a high mass system, like a heated concrete slab, it takes hours to cool down and hours to warm back up. You can't just bounce the temperature up and down on a daily schedule with high mass. It's futile. Every hydronic system seeks two states: thermal equilibrium and hydraulic equilibrium. Basically, the system naturally finds a point where energy in equals energy out, and pump pressure matches pipe resistance. But here's the kicker. The system doesn't care if you're cold. It just wants to balance. Our job is to design it so that equilibrium happens at a point where you are actually comfortable. Designing these systems isn't a straight line, it's a loop. We call it iterative design. You make an initial guess on pipe sizes and pumps, run the math, see if it works, and then usually you have to go back and tweak it. Maybe you need a bigger pipe here or a smaller pump there. You repeat this until the numbers look right. Let's look at this simplest layout, this single series circuit. One pipe looped through every radiator. It's cheap and easy, but there's a catch. The water gets cooler as it passes through each radiator, so the last room in the loop gets cooler water than the first. You have to size the radiators differently to handle that temperature drop. To get a bit more control, we use one-pipe systems with diverter tees. These tees scoop a little water out of the main loop, send it to a radiator, and then put it back. This lets us control individual radiators without stopping the whole flow. It's a clever way to get some zoning without running separate pipes all the way back to the boiler. Okay, this is probably the most critical concept for modern systems: hydraulic separation. When you have multiple pumps in a system, they tend to fight each other. One pump turning on can mess up the flow for another. Hydraulic separation, using things like closely spaced tees or a hydraulic separator, makes sure each pump operates independently. It's like magic for system stability. So, how do we achieve this separation? The classic way is closely spaced tees, literally two tees right next to each other. But recently, we're seeing more hydraulic separators. These are vertical canisters that not only separate the flows, but also remove air and dirt. They're incredibly useful, especially when connecting new boilers to old piping. Another common way to zone is using valves. You have one big pump and little motorized valves that open or close for each zone. But wait, if only one zone is open, that big pump is pushing way too hard against closed valves. That's why we often need a differential pressure bypass valve, or better yet, a smart variable speed pump that slows down automatically. Now let's talk parallel piping. In a direct return system, the water takes the shortest path to the first radiator and comes straight back. The problem? Water is lazy. It wants to go through that first short loop and ignore the radiators at the end of the hall. You have to use balancing valves to force the water to go the distance. To fix that lazy water problem, we use reverse return. Here, the first radiator supplied is the last one to return. This means the total pipe length to every single radiator is about the same. It naturally balances the flow, so you don't have to fiddle with valves as much. It uses a bit more pipe, but it works beautifully. This one is gaining a lot of popularity: the home run system. Think of it like an electrical breaker box. You have a central manifold, and a dedicated flexible PEX tube runs to every single radiator. It's fast to install, easy to zone, and actually uses less pump power than you might think. It's perfect for modern construction. We mentioned hydraulic separation earlier. Primary-secondary piping is the granddaddy of that concept. You have a main loop circulating water, and secondary loops tapping into it for specific zones. This is how we handle complex systems, like having high-temp radiators and low-temp floor heating in the same house. Each loop does its own thing. We always talk about boiler efficiency, but what about distribution efficiency? How much electricity does it cost to move that heat? Hydronics shines here. A good hydronic system can move nearly 6 times more thermal energy per watt of electricity than a forced air system. It's a huge operational advantage that often gets overlooked. And then you have the monsters, hybrid systems. This is where we take a little bit of everything, manifolds, PS piping, buffer tanks, and mash them together. It looks complicated, but if you break it down by function, it's just a series of simple concepts working together to handle things like solar input or multiple boiler stages.
So to wrap up, there is no single best piping system. It depends on the building. But whether you use series, home run, or primary-secondary, the rules of physics don't change. Respect hydraulic separation, balance your flows, and keep an eye on how much power your pumps are using. Do that, and you'll have a system that lasts.